Hey, I'm Harshul, and this is a quick presentation about the research I've been doing at Beaverworks this past summer. So, a little bit about myself. I'm currently 17 years old. I'm a rising college freshman studying CS, and I really love game design as well as artificial intelligence and machine learning, which is why last summer I participated in the Serious Games with AI course alongside Rob, and I really loved the community. It was super fun. So, this summer I returned as a TA to help Rob with the course as well as work on this research project in my free time. So, a little bit about the research. Last summer, I was really interested in the reinforcement learning we learned at SGAI, and I really liked how we could teach a model to, again, pick the optimal actions just based on putting it through lots of trial and error. And I wanted to apply this kind of technique to something new I was looking into, which is LLMs and prompting them efficiently. And I wanted to see whether there was a way I could train an agent to effectively, I guess, prompt an LLM by training it with reinforcement learning. And I kind of wanted to see like what is the minimum information you needed to provide in a prompt to make it a good prompt. And I guess when we get to more complex problems, like when do we know which techniques to use? Like when do we use chain of thought? When do we tell a model to think step by step? When do we tell it to act as an expert, right? So these are just some of the things I was interested in researching this summer, right? So a little bit about the process. I kind of wanted to prioritize building something functional over something that was perfect. So one of the first things I went through was just building a really functional framework as soon as possible just to start testing. And then after that, I just iterated on it to improve it and fix any bugs. And some of the key tools I used were Olama, which was really good for loading LLMs onto my computer, PyTorch, which is critical for training my reinforcement learning model, as well as Transformers and Peth for some of the more advanced stuff I did at the end. But for my initial stack, I used a pretty basic setup. I used a Q-learning setup, which is just a table that has values that tells you how valuable each action you can take in a state is. I used a pretty small LLM, Qwen2, with 500 million parameters, a pretty limited lexicon. So instead of giving it any words you could ever produce or think of, I just gave my agent some set of words you could pick from, and I made my own custom eval suite for. In this case, I made the task solving the Fibonacci problem, and I wanted to see if my agent could come up with the prompt code a function to commute nth Fibonacci, right? So one of the biggest roadblocks I faced was just that with this many words in the lexicon and using a Q-learning setup, right, the table would have however long this list was to the power of 6 or however long my prompt was, different states. And the problem with that is that my model couldn't really, again, explore all of those different states and would get stuck in local maxima and I'd be repeating a lot of words and not really come up with a constructive prompt. And in addition to that, the table was just using up way too much memory. So afterwards, I switched to a deep Q learning setup, which instead of using a Q table to represent all the states, I would just use a neural network so that when I passed in some numbers that represent each state, I would just get some output that represents the Q values for that state. So instead of having a table store everything, it's kind of like having a function that given an input of states can return the, I guess, intended Q values for each of the actions you can take. And another thing I changed was that I wanted to reject the duplicate words. So instead of the prompting Fibonacci, 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 it would actually have to pick different words each time to make sure the prompt wasn't just gibberish. I also wanted to strengthen the rewards a little bit just to make sure that when something good happened, the model really knew something good happened, and if something bad happened, the model really knew something bad happened. The only problem with this is that even though I increased these rewards, it was kind of difficult to differentiate which word was responsible for like the good reward, right? So I couldn't really assign the blame for it, and I had to think of a system to actually, I guess, show which word was responsible for success or failure. So that's why I wanted to update the system I was using for rewards, and I created this cool attention system where each reward for each word would be weighted based on a calculated attention score for each word in the prompt. I'll explain it a little bit more on the next slide, but using the system really helped, and I was able to converge on a successful prompt. I changed the task from Fibonacci to checking if a string is a palindrome just because it's a little bit more unique, and I couldn't just get to that by typing the word recursive into an LLM. So this prompt does look a bit funky, code palindrome string check if is, but the order of the words that matter, the actual context gets across, and the LLM is able to solve the coding task most of the time. Okay, so like I mentioned, I used I guess, an attention system. You can also call it importance, whatever you wanted to refer to it as, to, I guess, calculate how important each word was to the actual output. So the way I would do it is that I would take the prompt, I would calculate what the LLM takes out of it, and then for each word in the prompt, I would remove it and pass in the new prompt. I call it the perturbed prompt, just by removing one of the words, and just calculate how similar the LLM output was for each of these new perturbed outputs to the original output. And then the more similar outputs will get a low attention score because removing the word didn't have a really big impact. So the actual reward shouldn't be as high for it because it didn't really change the output. And if it has a high attention score, so which means it changed a lot, it just means the word had a high impact on the output of the model. Therefore, the reward that got given, whether it's high or low, should be scaled appropriately. So doing this made it a lot easier for me to actually figure out, okay, which words were actually important and impactful and which words were just fillers. So this is what really enabled me to get to this prompt because otherwise I wasn't really sure how to filter which words. So here's just some results, right? So when I additionally did this with the Q table, it was really bad. A lot of my rewards were negative and I wasn't really seeing much, I guess, progress. I had a few positive results, right? But most of the time it was below 0. So I knew I had to switch to the deep Q learning setup, to make sure I could actually explore more. And it did help a little bit. I was able to get more positive results overall. I strengthened the results, the reward signals a lot. So you see some of these really good cases. I think this hit the max actually. But I did have to switch the task because when using the Fibonacci task, right, the word recursive would mess it up a lot and ended up not being able to converge to a proper prompt. But when using the palindrome system, it was able to get a lot more positive rewards, but it wasn't able to really reach that maximum, which I was able to reach using the attention system because we were able to figure out, again, I guess, weed out the words that weren't really helping and focus more on the words that were. So there were a lot of successes here, but they weren't as high as possible. And I know it's not always high, but it was able to get a lot more, I guess, maximum results when I did use this attention system. So some things I'm planning on working on next for this project is just expanding to more complex problems, right? So Sweetbench is solving GitHub issues, and these are both just more complicated math problems than just running a simple function. And I wanted to expand from using an RL agent with a fixed lexicon to instead training an LLM using reinforcement learning. So it's just that it can pick any word and just has to figure out what's the next best word. So I want to look into more interesting techniques in the future. Something I've been looking into was group relative policy optimization with low rank adaptation, which is a technique people use to train LLMs using reinforcement learning. And I had some ideas about how to actually implement this, but I'm not going to get too deep into it. And I just wanted to say, before I finish my presentation, some acknowledgements. So I wanted to thank Rob Cedar and Joe Kurikar, obviously, for mentoring me throughout this, as well as thanking Charlotte Zhao for actually helping on the project a little bit and inspiring me to actually use these more complicated data sets, including GSM8K and MathQA. But thank you for listening. And yeah, that's been some of the stuff I've been working on this past summer.